most of you probably think of information as a part of computer science. But today, we will learn that information is a full-fledged physical substance, which, along with energy, space, and time, participates in physical processes. The term information was perceived only as an auxiliary quantity, which described something completely different from what we now mean by this concept. Much later, people began to talk about information as having the right to its own physical existence and being an independent physical entity. Scientists needed to find some clues in order to figure out what information really is. One of the first serious theories that actually started to work with information was the idea of Claude Shannon. This is, so to speak, the ancestor of everything we know about information and about informatics, which studies information as a certain fact. Shannon proposed describing information using bits, bytes, and so on, employing the constructs of 0 and 1, and using the approaches of yes or no. In reality, the process was, once again, much more complex, multifaceted, and lengthy, but it is important for us to understand that it was from this moment on that information acquired a certain method of measurement. In fact, this method of measurement was so successful, effective, and functional that today almost all the systems we work with, almost all the systems that exist, almost all computer hardware, almost all computer networks, even the video transmission that is happening right now, all of this is directly connected to Shannon's ideas. These ideas, based on yes or no, or 1 and 0, are precisely what made it so comfortable and reliable to work with information. At the same time, a very interesting approach to information was emerging as a measure of our ignorance about the world around us, or as a way to describe the amount of data, essentially, about what we are studying, what we see, and what exists around us. This directly pushed the idea of information toward entropy. And from about that time, information has come to be seen as something of a synonym for entropy. Let me remind you that in the classical sense, entropy is how little we know about a system. Well, some people rephrase this and say it's how much we know about a system. Essentially, it's like the joke about one eye and two eyes. It's probably quite appropriate to tell it here. The fundamental meaning doesn't really change. And so what's the most interesting thing here? That, essentially, we're talking about physical concepts, connecting them with entropy, and saying that physical phenomena are directly related to information. But how can they be related? That's probably the most interesting part. We take a step forward. As these ideas developed, experiments like Landauer's appeared, which you've all probably heard about. You may know that when we erase information, when we clear a computer's memory, a certain amount of energy is released. For a physicist, this means only one thing. If we are working with information, then in some incredible, miraculous way, we are also interacting with energy. And wherever there is energy, there is also matter. And where there is matter, there is mass and everything else. And all of this, as a rule, twists into an incomprehensible spiral. It could only be simplified if information didn't behave this way. That is exactly why I said unfortunately, because there is no simple term that would imply we are just working with numbers on paper, a term that would describe information solely as something located somewhere. Later on, we will return to the questions of what and where. We have moved on to the idea that information is a certain physical entity. There is a lot that could be said here about Landauer's experiments, about his approach, but again, in order not to dwell on this for too long and to distill the main point from everything we are discussing, we will say just one thing. Information has turned out to be quite a physical entity. It turned out that changes in information directly affect the behavior of a system, and the amount of information apparently determines not only entropy in some unclear way, but directly influences the physics of a given process. In other words, since the time when Landauer conducted those famous experiments, it has become clear that information is connected to physics. The only problem was that it was completely unclear how they were connected. So, logically, if we have a certain link consisting of the information of a physical system, and all of this is tied to entropy, then in order to have the lowest entropy, we need to describe this system as fully as possible. To describe the system as fully as possible, we need to expend the maximum amount of energy. Therefore, the fewer parameters we need to determine, the less energy we need to expend. Or, to put it in even more physical but veiled terms, the more vividly a system manifests itself in this reality, the less energy we need to interact with that system. At that time, this principle had not yet been addressed within physics itself, but it became the foundation for Landauer's understanding of a process we are all now quite familiar with, the process associated with the fact that when we erase information from a computer, when we erase information from a chip, we somehow get energy from an unknown source. This connection was known, but it still has not been explained. And here, perhaps the most important result was that we began to perceive information as a real physical entity. We realized that information, energy, and all other fundamental physical concepts interact with each other, exchanging something unclear among themselves. A bit later, I will return to this question again. And they represent a unified system. Essentially, measuring a system leads to us influencing that system. But how can we influence it? Well, many sources interpret this as the interaction of an instrument, the interaction of some measuring device with the object we are measuring or studying. This is a good approach, but the criticisms of these approaches are usually quite valid. They point out that in many cases we have no direct interaction with the objects at all. Nevertheless, the process of measurement exists. Still, the observer paradox, which is better not called the observer paradox, is also noted. And there are many examples that confirm this paradox. Well, sometimes, for those who perceive this process exactly as we have just discussed, there is really nothing to argue with. That's why it's usually said that the process of measurement consists not so much of the object being measured, but rather of a group made up of the setup of the object itself and a certain unspoken exchange between these entities. If we're talking about information, then in some mysterious, clever, almost magical way, this information by itself changes the system. And essentially, we are not just measuring the system, we are obtaining information about this system. And if we recall Landauer's principle, if we remember what we said about thermodynamics and about the interaction of information with physical objects, we can easily draw parallels and say that the very process of measurement will inevitably affect this system. And here the physics of information supports us. It turns out that if we perceive information as a certain physical entity, an entity connected to energy, an entity connected to matter and other objects, we can confidently assert that obtaining information will alter this system. And since the quantum level is so subtle and sensitive, any movement at this quantum level, any attempt to extract information from the quantum level, leads to us getting exactly what we get. We encounter a phenomenon known as the observer paradox, the measurement paradox. Perhaps the measurement paradox can be explained precisely in this way. At the very least, Landauer's principle now helps us do all of this. And essentially, knowledge about the system itself does not change the system. But manipulations with the entropy of information and the entropy of the state lead to us, in fact, touching this system in one way or another, probing it, and returning Schrödinger's cat to the state we need. And even though there is this strange peculiarity involving quantum superposition, what matters to us is that the very fact of the object's interaction with information allows this interesting phenomenon to manifest. And now we say that, in addition to having energy, in addition to having space-time, in addition to having entropy as a measure of all this, we also have information, which is a rather strange physical entity, but also a starting point for our reasoning. We can say that without information, nothing exists, that any action, any movement, any manifestation of anything at all will, in a physical sense, provoke the emergence of this information. Physics is more reserved in this regard. Physics describes information as a certain property of a specific system, and physics always ties information to an object. That is, if we proceed from a strictly physical approach, then information does not exist without matter. Matter can be anything. Instead of matter, you can substitute any physical phenomenon, but it's easier to think of it as a symbiosis of matter and information, and to perceive information as a part of all this. And one more thing, perhaps I'll say this separately once again. So we said that it seems like information describes the state of an atom, but as I understand it, this approach is fundamentally incorrect. It's not that information describes the state of the atom. It's just that we have a certain connection between the particles that carry information and what is inside the atom. And essentially, we're not talking about information determining the structure of the atom, but rather that information is tied to those particles that interact with the atom. But in any case, all these considerations lead us to the most interesting point of our entire conversation today, or better yet, monologue. Although I hope that you are also listening and asking yourself some questions, so it's as if we're having a conversation. And now we've come to the main, most interesting and most difficult question. So, essentially, what is primary in the universe? Information or matter? Information or some kind of physical objects? What comes first? Information and then matter, or matter to which information is attached? Well, we've already understood quite well how classical physics describes this. Actually, not just classical physics, but physics in general. In physics overall, information is always tied to some kind of object. In physics, information by itself does not exist, and no one has dismissed the fact that information sometimes manifests itself in various strange ways. How can this be explained from the perspective of the current paradigm? Well, actually, it's quite simple. We are simply interacting with those layers of reality that are still beyond our control, unknown to us, and which we cannot yet perceive. So in those cases when it seems to us that information behaves as an independent entity, it is very possible that we are dealing with entities that we are completely unfamiliar with for now. For example, it is possible that information is tied to space and time, or to space and time separately. And in general, it's not really important. This whole space-time concept always wants to merge together in our minds. For us right now, that's not so important. What matters to us is something else. Essentially, information can be a characteristic of space-time, And matter, which exists in spacetime, can be a derivative of spacetime and the information about that spacetime. This only means one thing: even without violating the approaches we already have, we can always return to the principle that any object in our reality is an interaction between information and energy, a principle that has been stated many times, a principle that repeatedly manifests itself, and a principle that is often referenced in simulation theories and other, let's say, less popular scientific theories that attempt to describe the structure of our reality. But do you know what's most important here? I think I've come to one of the main conclusions, which to me personally seems to be the most important. We've reached an interesting point. Once again, we've run into the fact that physics doesn't understand what information actually is.
We have these fragments of knowledge that we keep discovering everywhere. We have an understanding that information always seems to be tied to some object, no matter which one. We know that there is always some kind of information carrier, and that information itself, on its own, apparently does not exist. At the same time, we cannot deny the existence of a universal informational field, or, let's say, some fundamental entity that contains this information, or is able to work with it. But we also cannot confirm that it exists. However, in the processes known to modern physics, in those processes where information manifests itself, we always see that information is directly connected to some specific carrier. It doesn't come out of nowhere, it always arrives with this carrier. And as an example, I mentioned the strong interaction in the atom. Inside the atomic nucleus, this strong interaction involves the exchange of particles, and these exchange particles carry information with them. We can examine many factors, and such interactions, phenomena, and exchanges of information will always imply the presence of some object that transfers this information. We also found that the very idea of the physicality of information most likely arises in our minds because we imagine information as some kind of material object, like a sort of jelly poured into a pot. No, this idea is about as accurate as thinking of light as being made up of little balls. It's not entirely correct, and it would be more accurate for us to understand that information is still attached to something. But what exactly is it attached to? That's a good question. It could be attached to such a subtle level that not only can we not work with it yet, but we can't even detect it for ourselves at this point. Perhaps this subtle level is actually synonymous with what science fiction refers to as the information field of the universe, and maybe it is precisely this informational level, or this subtle field, that will explain various complex interactions. For example, quantum entanglement itself, where one atom can be here and another somewhere far away, a million light years away from us, and their states change instantaneously. On the other hand, quantum entanglement itself is characterized a bit differently today, but we'll talk about that separately another time. And now we come to an interesting state where we've talked a lot, but in the end, we still haven't really understood anything. Unfortunately, we also don't understand what is primary, but we do understand well that in the paradigm of modern physics, in the way science describes it, there must still be some kind of matter, some object that carries this information as the primary element. As for what kind of object this will be, we still don't know. One way or another, I wouldn't dismiss various alternative and interesting theories, which can also tell us a lot of fascinating things. And the theory that follows from the simulation theory, where we perceive any object as information plus energy, has a certain promising potential. Moreover, now we know that the notorious observer effect, or the manifestation of quantum measurements, this manifestation of the system's abnormal behavior, which changes literally just by looking at the system, is connected to the fact that in order to obtain information, we need to expend energy. This fits with all the other laws and is perfectly consistent with the knowledge we currently have about quantum physics.